What you are looking at is a modern high-density server rack. A single row of these machines consumes enough power to run a small neighborhood, processing the data that keeps global financial, medical, and logistical systems operational. But the availability of that computing power relies entirely on a continuous, perfect flow of electricity. If the current drops for even a fraction of a second, the servers shut down and the data stops moving. The raw utility power delivered by the public grid cannot provide that perfection. It is inherently dirty, volatile, and prone to sudden interruptions. To bridge that gap, engineers use a single-line diagram. This schematic is the architectural map used to design the electrical infrastructure from the grid directly down to the server rack. Let's look at the components, starting at the rack and tracing backward to the Power Distribution Unit, or PDU. Continuing upstream, the PDU draws its power from the Uninterruptible Power Supply, or UPS. The UPS, in turn, is backed up by massive on-site generators. Finally, the generators connect outward to the primary high-voltage utility substation. This creates a complete linear delivery chain from the public grid to the processors. This pathway acts as a meticulously calculated chain of risk mitigation. Every node you see here exists to physically filter, bridge, or manufacture power before it ever reaches the silicon. Achieving a continuous 99.999% uptime requires stripping away luck and replacing it with rigorous mathematical sizing and engineered redundancy. We begin building our model at the very end of the power path, the physical connection between the PDU and the server rack, to determine required capacity. Sizing this infrastructure incorrectly by even a small margin leads to overloaded circuits, cracked breakers, and physically melted copper cables. To safely size the system, engineers separate the electrical draw into two distinct measurements: real power and apparent power. Real power, measured in kilowatts, represents the actual physical work being performed by the server's processors and cooling fans. Apparent power, measured in kilovolt amperes, or kVA, represents the total volume of electrical power the infrastructure must physically carry. Due to electrical inefficiencies, the apparent power is always a higher number than the real power. This vector diagram, the power triangle, shows the math to calculate infrastructure requirements. Alternating current creates wasted energy, reactive power. As reactive power increases vertically, it forces the apparent power hypotenuse to stretch longer than the real power baseline. If you size a PDU solely based on the server's kilowatt rating, you guarantee that cables and breakers will be critically undersized for the actual kVA load flowing through them. Precision in separating real from apparent power provides the mathematical guarantee that the physical wires will safely handle the load. Moving one step up the single-line diagram brings us to the uninterruptible power supply. This UPS block diagram shows power conditioning. The system acts as a firewall against voltage spikes. Through double conversion, the rectifier flattens erratic AC into DC. The inverter then reconstructs it into a perfectly smooth AC sine wave for the servers. The second role is serving as a time bridge. The battery bank provides critical millisecond power to keep servers alive during an outage, while massive backup generators physically spool up to speed. Selecting these batteries requires engineers to balance the physical facility footprint, the expected lifespan of the cells, and the initial capital expenditure. This scale comparison illustrates the divide. On the left, traditional lead-acid batteries require massive amounts of dedicated floor space. On the right, modern lithium-ion cabinets. Facilities are rapidly shifting to these lithium-ion chemistries. They provide much higher energy density and longer operational lifespans, justifying higher upfront installation costs. The UPS operates as a continuous active filtration system and the most critical temporal bridge in the entire power path. Zooming out to view the entire engineered path reveals a hard truth. No matter how perfectly a single path is designed, individual components will eventually fail or require physical maintenance. To counter this, engineers use redundancy topologies. These are mathematical risk tolerance models that dictate exactly how much of the power infrastructure must be physically duplicated. This N-capacity diagram shows the baseline. A single failure causes a blackout. N+1 adds a parallel module to absorb flow during failures. 2N builds two completely mirrored power paths. 2N+1 combines both, giving each independent path internal modular redundancy. Moving to higher topologies like 2n+1 exponentially increases capital costs and real estate requirements, but it is strictly required to host critical global infrastructure. Redundancy topologies are how engineers physically install mathematical guarantees, ensuring that isolated failures never impact the final server rack. The theoretical architecture of the diagram eventually translates into physical reality of installed metal and copper and thick electrical enclosures. Securing this physical equipment requires understanding the distinct difference between grounding and bonding, two terms that engineers frequently confuse, despite them serving entirely different safety functions. Grounding is the physical connection linking the electrical system directly to the earth via a rod. It provides a safe, direct clearing path for catastrophic electrical faults. Here, the green grounding wire routes to earth. Bonding uses bare copper jumpers to connect metal enclosures, equalizing electrical potential to prevent lethal shock hazards. These enclosures must also be sealed against environmental threats, requiring strict ingress protection, or IP ratings, to keep out conductive dust and water. Once the infrastructure is installed, its health does not remain static. Ambient heat and microscopic vibrations cause physical degradation to the connections over time. This thermal camera view demonstrates thermography. Infrared scanning allows technicians to actively detect ham resistance connections, like this white-hot breaker lug, before catastrophic arc flashes occur. In parallel, engineers run power quality monitoring to detect invisible harmonic distortions that slowly degrade UPS components over months of operation. Proper bonding, IP ratings, and thermography actively validate and protect the physical integrity of the power path we just modeled. Observe our completed 2N architecture. Utility power flows down feeds A and B. Suddenly, a grid failure cuts primary power. Instantly, perfectly sized UPS batteries bridge the gap, absorbing the full load. Seconds later, backup generators activate, taking over the apparent power and restoring stability. The facility survived a catastrophic event uninterrupted. Real and apparent power were calculated flawlessly, and the entire chain was isolated through a 2N redundant topology. Continuous uptime is mathematically engineered and protected at every node, from the massive high-voltage grid down to the final layer of silicon.